Okay, here we have a picture of some glasses filled to different heights with water. This is sometimes called a water glass xylophone, okay, because they give you different frequencies, as we'll demonstrate here. So there's an air volume here, and if you blow air across the top, what you do is you excite sound waves, and here it sets up a standing wave, and this is the lowest frequency standing wave. The molecules don't move here, and the molecules are moving fast here at the opening. And then if you fill it up with water, there's a shorter distance for setting up standing waves, so the wavelength is shorter and the frequency is higher. As you go from here to here to here, the frequency is higher here. There's a high note here and a low note there. Now, so we have 3 wine glasses here. If we take a look at this, now you may not have 3 wine glasses, but I'll tell you, let me what the heck here. Ordinary glasses will work just as fine. Okay. Now, first off, these are not particularly high quality glasses, but in any case, let's see what kind of frequency they ring at by hitting one of them. So let me do this one. Okay, it looks like 939 hertz. 939 hertz. Let's see what this one does, the second one. 972 hertz. And this one? 1001 hertz. Okay, the frequency that lasts the longest is 1001, which is right there. So there's a lot of frequencies here. Now, let's excite this by blowing over the top of it. So I had here's the straw. No, yeah, here's the straw. I wanted the long straw here. Where's the long straw? Okay. Oh boy. Okay, I'll use this straw. It's less convenient, but it's anyway. So I'm just gonna blow across the top of this, just like we're gonna blow across the top of that. Blow across the top of this and see what frequency components there are. Like 680, I think. Okay. And here, 681. And this one, 678. All pretty close, okay? Because they're all the same depth. So that's about 680. So let's fill it up halfway with water. So we're doing this now, so let's do this. Fill it up halfway with water. And so there's about half as much headroom there. 1,050. 1,060. So the frequency is higher here because the wavelength is shorter. The wavelength is forced to be shorter. It can only be half a wavelength or quarter wavelength, can be no longer than this. So the wavelength is shorter, and so therefore the frequency is higher. Okay, so now conversely, so you can set up a standing wave in the air, but if you tap the glass itself, like I will with our metal ruler, it sets up a standing wave in the water. And here in the water, here's a quarter of a wavelength here, and here's the lowest frequency standing wave there can be here. And actually I didn't draw it right, but let's not worry about that. So this is going to be a low frequency, higher, higher, and yet higher frequencies. So let's do these. I'll do this one will be a little bit. That'll be more. And oops, I won't be breaking all of them. Here's more. Okay, so let's put them in order here. Okay, so here we go. So there's a long wavelength, low frequency, shorter wavelength, higher frequency, shorter still, very high frequency. So let's see what we've got here. Did you hear that? Low, medium, high. Low, medium, high. Okay. Now I can try. We can get the spectrum analyzer on here and see what we've got. So here, well, it looks like 759, 880, 966. Okay? So, now, okay, so now if you had a whole array of cups, glass, wine glasses or whatever with different heights of water, you could actually play a tune here because you could have as many notes as you have glasses of water. So, okay, so that's